thanks everyone for coming again. So less people this time, but yeah, still good, right? Only best ones.
Must be the weather.
Yeah. Today we'll have a here talk from David about his project, and yeah, his company was super kind even to like pay for this pizza. So thanks, and if you want to say something about it.
Yeah, so
Very good pizza, right?
yeah, pizza, and we also have some hats there that you can. I see that you have already taken a few of them. The company is called Reactor. We work here in Amsterdam. Now we have a new office. If you want to know anything else about the company, just let us know, me or Lisa.
I'm here.
I'm very, very proud of like working for a company that actually like care about sponsoring a Lisp meetup. So really, really nice.
Oh shit.
So thanks. Let's just start maybe with the talk. So firstly, I have a problem because like I have some notes in the presenter mode that I cannot use my laptop. So I will try to like make it on my way. Just if you have any questions or something, just stop me and let's discuss it. Let's keep it conversational.
I have a question.
Yeah.
Is this the world premiere of this talk? Is this
Yes. Okay. So yeah, first a little bit of me. So I'm David Vázquez. I have been in Amsterdam for 3 years. Having a Lisper, I think, for more than 12 years. Actually, like yes, like 12 years. Yes. I started with Image Lisp, then Scheme, Common Lisp, and basically for like 10 years I only did Lisp until like 2 years ago, and then for work I started working with JavaScript and other languages. I have also some Fork, but like mostly Lisp. But like today I'm here because like I wrote like JSCL. That was like in 2011, actually at the very end of 2011. And a little bit of the context, because like some people like said maybe that some of the goals of the project were not very clear, so the context I think helps to understand why it is like it is. Back then when I started this project, I have written at least 2 interpreters, one for Scheme and one for Common Lisp, and a compiler from Scheme to native code. But I could not bootstrap this compiler. It was quite frustrating, like after so much work, and I lost the code. I don't know where it is anymore, so that was frustrating. And also, I wrote a 4th implementation, bare metal. Again, everything in 4, but I could not bootstrap it. So the whole point of this project was just, I want to do something very, very simple that compiles itself. That was the whole point of it. No performance goals, nothing at all, just compile itself. That was initially, of course, then you changed a little bit the project, but as it early bootstrap. We will see later, but yeah, I think bootstrapping the project was quite easy and fast. So let's start a little bit like basic Lisp that we support at the very, very beginning. I guess, like the audience knows quite a lot of Lisp, so it's not going to be very useful for you, but we will start with some integers, some strings. We have symbols, some special forms. So the 3/4 of them, they are atoms. They are like, you cannot split them. That's basic unit of like data. And then those ones are lists. I don't know if you can see very well, but there are like parentheses around the elements of the list. On the right, you can see the value that you would get if you type this into your repo. Okay? So the very basic exercise that everybody in Lisp does is to write what they call a meta circular interpreter. That basically is making this transformation as the eval function in the language. Okay? So try to remember a little bit, like we have 3 cases like for some values that give their own value. And then we have a few like quote, if, lambda, and function call application. So I have like the basic case of like an interpreter, but before, like as I said, every Lisper does this at least once. Like it's a very, very common exercise. Yeah. I cannot say it better. So this is the code We're going to call the function eval. It's prefixed so it doesn't collide with the host function in the system. All this code is real. It's like you execute it and it works. The example that we will see later are like executed from here. The signature of the function is we have a form that is the expression that we're going to evaluate, we're going to get the value of. And we have the environment that is the set of values for the bound variables at some specific point. Okay, so the first case is, as we saw, if it's an integer or it's a string, it will give their own value. They're called like self-evaluating forms. Nothing very interesting here. So 2 will evaluate to 2, a string will evaluate to the string itself. If the form is a symbol, then we will try to find that symbol in the environment to get the binding. If it's there, we will return the value, otherwise we will throw an error. Okay? Here? Yeah. Now, if this means a non-empty list, then we're gonna dispatch a few cases looking at the first element of the list. So the cases are quote. It means just give me whatever element is after the quote symbol. Actually, that's a typo. It should be trace form, second form. Yes. Yes. It doesn't matter too much. If the first symbol of the list is if, we basically are gonna like delegate that to the host system. Just evaluate what is after the if symbol. Treat that as a condition. If it's true, we'll evaluate to the third one. If it's false, to the fourth one. Then we have lambda, that will create a function. And again, we're gonna just create a function in the host system that takes as many parameters as you want. And what it's gonna do is, with the values that you pass, it will extend the environment, like assigning those values to the parameters that you define in the function, and evaluate the value of the function with those new values. Does it make sense? Okay, and the last case is function application. So if the first symbol of a list is not quote, if, or lambda, we will just call that function. Evaluate the parameters and pass it to the function. Doesn't really matter, just try to keep a little bit like the structure. Like you have a few base cases, then if it's a list, you dispatch looking at the first argument, the first element of the list, and then there is a last case that is everything else is as a function call. Okay, so this is an interpreter, but the talk is about writing a compiler. But we're going to follow the same structure. We're going to convert this into a compiler. Is anybody a little bit familiar with JavaScript at least? Yeah. Okay, good. So, same structure. Same structure. So now the signature is the same, but instead of returning the value, we're going to return a string. We're going to go very simple. We're going to return a string that is JavaScript code that if you evaluate it, then it will give you the value. So eval now becomes call compile and then run the result as a JavaScript code. So if it's an integer or string, we're going to call this auxiliary function that we can show you later. That basically means take whatever value you have in list and convert it to JavaScript. For symbols, we will use the same plan, but now, of course, this happens at compile time. You don't have the value of the variable. So the value of the binding is going to be the JavaScript variable. So let's say you have a variable in list called x, and you map that to temporary variable 1. So it's just, we keep that mapping in the environment so we know how to reference the JavaScript variable. Oh, and again, we dispatch look at the first argument, and the compilation happens. Quote is, again, not very interesting. There is a typo, but and if, this is a bit more interesting.
I'm missing about the stuff up there, the symbol.
Yes.
I mean, you're not generating any code, right?
No. No.
So
I
what do you do?
Well, when do you add something to the environment in the lambda abstraction? So in lambda, we will see how symbols are added to the environment.
Yeah, but I mean, okay, well.
So you can imagine the environment is set, and your environment looks like the symbol x in Lisp maps to the string temporary variable 1.
Yeah.
And you assume that that variable exists in JavaScript.
Yes.
So to get the value of the variable x,
Yeah.
you want to get the value of the JavaScript variable.
Yeah, right.
Yeah.
Yeah. But you do that at another point. You do that later on, right?
Adding the variable to the environment, yes.
Yeah.
But referencing it is here.
But I don't see any reference. I mean, I don't see anything that generates any JavaScript.
No, well,
Or
this res binding, the value of the binding is going to be the string directly. So that's valid JavaScript code.
oh.
Okay.
Oh.
We will see now. I have an example
Oh,
because
yeah,
I understand
I
the code is quite difficult
Of
to
course,
understand.
yes.
But we will give
Yeah.
some inputs and
I
we will
think I
see
get it, yeah.
how that works.
So this,
So-
so this
yeah.
function returns the string.
Yes.
Okay.
Right.
The function always
It
returns.
returns
Yes.
the JavaScript string from the binding in the environment.
So this case is really interesting. So how do you compile that conditional? This is a tertiary operator in JavaScript. You see there are some parentheses. This is not our list. This is just strings. And what you do is, okay, compile the condition in the same environment. The consequence or the alternative branch and put together in the JavaScript operator. Why not if? Why the tertiary operator? You want to compile always to an expression, not statements. The idea is because it's recursive, I mean, expressions compose very well. You always can use a value that, and you just follow the tree and you get the value that you want. But if you compile to a statement, then what do you do with that?
It's the end of the line, yeah.
And that's a big limitation because in JavaScript some things are statements. Like you cannot get the value of throw, you cannot get value of like many things.
Mm-hmm.
So there are some tricks to actually always generate an expression. But as you can imagine, this is going to generate a lot of extra unnecessary parentheses as well. Right? That doesn't matter.
No
The
such
goal was
We're used
just
to
to
that.
bootstrap it. The goal was to bootstrap it as fast as possible.
You're not supposed to read it.
We will fix that later. Or not. So, lambda, a little bit the same thing. What you do is to generate a function, take all the arguments, concatenate them, put a string, compile the body with a new extended environment. You see, and then we can generate the symbol. We use the symbol, the string of the name of the symbol as a JavaScript variable. And again, that's an expression that you can take the value of. Any question? If you see, like, this code is really primitive. Like, it's not using the structuring, it's not using anything fancy, and that's completely intentional. We want to keep it simple because the goal is to bootstrap this thing. The more sophisticated technology you use, more work is going to take you to get that to compile itself. So it just no effort handling or anything, just take second, third of the list and all these things. Okay, and finally, function call. Same structure. Compile the first part of the list, compile all the arguments, concatenate them together, put a comma, and call it. Okay. So I said like dump, that will just. This is using a bit more like sophisticated technology, but if you think of like format can be replaced with a like print digit to number to string or something, and that's what happens in the original code. There is some problem with this, we will see later, but basically this works. So this is an example. You compile, cannot see very well in the slide, but there is a quote, and this lambda expression that is basically like ensure that the argument is a list. And it compiles to, compiles to that thing. As I said, a lot of redundant parentheses, but it works.
Const p returns a function, or
Yes, you assume that that's available in JavaScript. It's a primitive function.
Oh.
So, of course, in addition to the compiler, you're going to have like a runtime set of functions that you provide in JavaScript. Okay? So that's really simple. It works, but we need some extensions because, like I just saw, like some of the utility functions that we use are going to be a bit sophisticated. So I separated variables into two namespaces, like for functions and for variable value. Add a global environment, set q and set f set q. That's not the standard, but I use it like to assign and mutate the variables. In this case, for a function value.
Function slot.
Okay, and this is a problem that I had very early. Like, if you go back to the utility function, we say that if you see a list, we compile it to a JavaScript array. But there is a problem with that. That if you evaluate that twice, that's going to give you two different arrays. So as soon as you introduce f set q or set q, you have mutation, means that you need a concept of identity. So that is a problem. You should fix it. So basically what we do is we extract the value outside of the function and we return just that value all the time. I will show you later because it's easy to do it in the REPL itself. Okay? And if you look at the code, we have used some things that are not in the definition and or the found count case. So what do we do with this? You can actually add it to the compiler as well as extra cases. And I think it's what I did initially, just to bootstrap it itself. But of course, those are macros.
Yeah.
So just add support for macros to the compiler. Just that. But there is a problem when you add macros to the compiler. So as soon as you have some macros, the macros are evaluating code in the host system, not in the target. So now you have some state. So if you want to bootstrap that, like every macro that you define is in the host system, but it's not in the target system. So you will need to dump that. So recreate that in the environment. That's a little bit the tricky part of the bootstrapping process. But yeah, you can see a little bit like in this case, like this is a define macro, and this eval when compiled, that compile define that's executed in the compiler at compile time in the host system, not so you don't have access to JavaScript there. So basically, define will mutate the state of the compiler. So what we do just is we take that state and dump it as an object and put it in the interpreter and in the destination system, so you can load it and recover all the macros that were defined. And that's a curiosity, like this is the definition of def macro itself. You cannot use def macro, of course. So okay, so as I said, for bootstrapping, some complications like macros are functions that are executed at compile time. They mutate the host system, so we have to recreate that environment in the target system. Okay, so now after this you have a working compiler. This pass expression, you can mutate things, and it will give you JavaScript, and you can execute it. But you still rely on the reader of the host system. Yeah, if you want like a REPL to work in the browser, you will need the printer and the reader. And yeah, that's something that I also did. Implemented that very simple reader. Eval is just the compile function, then evaluate it. I wrote a very simple printer. And this is the result. So it took 3 weeks of work after like 1,300 lines of code, including comments and everything. I created a tag in the repository. So in case you want to play with this or you want to create a new list, just fork it from that tag and play with that. This compiles itself. And it's JavaScript, and the slides are also JavaScript, so there is actually a demo in the slides. You can use it here. This is the original version, not the current one. So it's pretty old, it's missing a lot of things, but it still is interesting. So let's try, for example, what happens if I do something like this. Okay, think what is happening there. So, I mean, of course, I didn't write that JavaScript code. I just took the compiler that I had in Lisp, passed his own code, give me JavaScript, put in the slides, pass more Lisp code, and it works. Okay, and there is something very interesting here. That's why I'm including the slide and not the new version. I have some functionality in this repo. If you pass a comma before the expression, it will compile it, but it won't execute it. It will just show you the result. Okay, so you can see how that.
It's like disassemble.
Yes, exactly. So how do this expression work? I mean, pretty bad code, but it works. That's the important thing. So, as I said, JavaScript has statements. So the first of the tricks is wrap everything into a function that calls itself. Then you can have statements inside. And everything becomes an expression, so it works with the compiler. Var x equal 1, var y equal 2. Of course, these two values are the compiled result of the arguments. If you make more complicated argument, you will see there in line. Some error checking, and then return the result. Okay. Now, another example, if I have a function that returns this thing, this is what we said. We want this to be true. Right? So what's the value of that thing? Let's see. See? So we extracted the list outside of the function, and it will always return the same object.
I think you're not even required to.
What?
Go on.
I think
The list was
maybe
crashing.
your laptop went to sleep mode.
Well, you just showed the most important part, I guess.
Yeah, he's back. So is there any expression that you wanna evaluate and see how or what compiles to?
Previous expression had some strange name. Was the first character L or 1?
Yes, for literals it's L,
Okay.
and variables are V, and then a number. Originally, I actually used the name of the symbol, but it was a bit complicated. I had to escape things like generate a random number. A number sequentially just add it there. And that number is also part of the compiler environment, in the sense that when you are compiling the compiler itself, it will generate a lot of random variables, like v1, v2, v3. When you bootstrap it, you cannot start v1 again, because that already exists. So you have to dump how many variables there are in the compiler, and then continue from there.
No, okay. Yeah.
Okay. But, okay, this is not Common Lisp yet. It's just... Not go to this one. Yeah. So, at that point, I had the... succeed, 13 days, I bootstrapped the compiler, but yeah, it was out of fun, so I wanted to continue.
What was the hardest part until this?
I think that getting your head around the whole eval, when and where things are evaluated.
Yeah.
You have macro, it's quite easy when you're in the same environment. You just define a macro and then use it, but when you're bootstrapping the compiler or you are cross-compiling something, suddenly the compile time means before you compile the compiler yourself, and eval time or load time is after, and that separation is quite complicated to understand.
Yeah.
Indeed, I understood that eval when I wrote this thing. Before it was I'm defining a macro, so I use eval when compile time just to get the function compile time, but you don't see how important that is until you write the compiler or you just generate the FASL files in a different time and don't load them.
What was the surprisingly the easiest stuff?
I guess the eval function. It was way easier than the reader. The reader is a bit messier because, of course, you don't have strings here. Everything is strings, so you have to get the first character and keep it track. That's why I didn't include in the slide. I mean, if you saw the compile function, there was 50 lines of code. The whole thing is 1,300. And anyway, so at this point, I wanted to do something more, but didn't know what. I didn't want to create my own list. It was completely out of the scope. So it's like, I considered a few choices with a friend, and we said, we could actually implement image list in the browser. That would have been very interesting, actually. So I don't know what we have done with that.
I can see where that is going.
It could have been very interesting, but we didn't. So we implemented Common Lisp because basically the documentation is also like hyperspec. If you have that, you don't. I mean, you can implement the language easily. And from here, it was pretty much easy. Okay. So some things that we had to change in the compiler. Special variables, like in the previous version, all the variables are just JavaScript variables. So we had to implement dynamic binding, lambda list, like first arguments, multiple values. The strings in JavaScript, for example, are immutable, which is a good thing, but they're not in this. You can mutate the strings. So that's also something that you have to change. We compile the strings to an array of characters. The downside, of course, is for the interoperation with JavaScript, then you have to convert the values. Control flow, that's also really interesting because in Lisp, the whole how it's structured is you have the higher level loop and all the do list macros, but at the end, they normally compile down to tag body and go. But you don't have Go in JavaScript. So I first actually tried to write a very smart compiler that kind of generate the graph of the control flow and reconstruct loops, but that's not always possible, so you have to see when it's possible or not. I gave up, it was too much work. It wasn't worth it because if you do the compiler too complicated, the output is going to be huge anyway. So you have to balance between having a simple compiler and generating good code. It doesn't matter if you generate very good code if your bundle then is 5 megabytes.
So your goal wasn't really to make a complete Common Lisp? Because otherwise you would need something like that.
No, I have tag body in Go, but what I do is I do a state machine. I have a variable with which is the label that is active, and then when you do Go, you switch that and return. It works, but it's slow. So what I do
so you don't
is
want to build on top of that.
Exactly. What I do is I have a while internal form that compiles to JavaScript while, and everything else, all the other macros are based on while, not on tag body. So and library, if you compile it and load it in my system, it will use tag body and Go, and it's slow. But if you use normal loops, then it's not a problem. But it's interesting. And I wrote a very small and simple JavaScript code generator. So the compiler doesn't generate strings anymore. It generates the JavaScript syntax, and then there is a small printer for JavaScript that removes all the redundant parentheses, and it uses right precedence information of the operators, and generates a bit better code. We could discuss many of those things, but they would be probably too long. So I can show you a little bit how special variables work in JavaScript. That's the next slide. So how do you compile dynamic variables to JavaScript? So let's say you have this let star, two variables, you want to bound them to two different values. So the JavaScript code is, again, we have a function, it calls itself. Oops, sorry. We have that S bindings, that the name came from, if I remember correctly, safe bindings. So what we do is we compile value1, and we compile the code to set value1 into the first variable, bind it, and then we add the variable 1 value to this S binding array.
Which is like a global.
No, it's in this function. So it's local to this let star.
But the var1 is outside the function, right? I mean, it's...
No, I mean, sorry, this is a Lisp code, and that's a comment, just to see. This is your Lisp code, and then the JavaScript code is here. And var is not global, it's inside this function.
Yeah.
So the function is to match the let star, and S binding is just an auxiliary variable inside. So what's the point of that? Go back to the let star. Imagine that when you are evaluating value 2, you get an error. You have to roll back only the bar1 binding, not bar2. Does that make sense? So maybe let me show you the whole JavaScript code. So first, bind variable 1, bind variable 2, then there is a finally, restore the bindings of S bindings. So you don't restore all the bindings unconditionally, but only the ones that were successful. That's why it's a bit tricky. Anyway, but the whole point of this is not the implementation, is that it's complicated to get it right.
So this JavaScript function already containing the environment, like the binding environment, and it's passed to the
Yes.
child function.
Yes.
Okay.
Well, I mean, it doesn't contain, it will add it. I add comments because it would be too long, but you could have here probably like a bar v1 equal value 1. Okay, but the thing is that for every special form that you have in Common Lisp, it's quite complicated. The semantics is not trivial. You have to be really, really careful, or then you will load some library and will fail. And there are still a lot of bugs everywhere.
Anyway, why there's extra parentheses after the value 1?
It's a comment, so probably made a mistake.
Weirdly.
It's a comment. In the comments, I don't have parodies, so probably made a mistake. Shouldn't write this in comments. Okay, so that's part of the compiler. But then you also have library. Like the Common Lisp library is huge. But not the core itself. So there are, I think, like 15 special forms or so. So they say like, oh, Common Lisp is huge. Then they complain that the scheme is too small. But actually, like, Common Lisp is quite simple to compile. The special forms at least. And then the rest is just library, and it shouldn't make anything more complicated than necessary. So, but the library includes very useful things like generalized places, condition system, back system, backward loop. Something really interesting is I implemented the first 3 of them, but backward is quite complicated to get it right as well. So I just took it from somewhere. And the same with the loop. Very recently, actually, like a year ago. Backward was written originally by JSCL, I think in 1984, 5 years before I was born. And the loop is like the same. Yeah, consider the comments of the beginning of the file. 1985. Yeah. Interesting. But it works.
But why was it so difficult to?
It's tricky. It's like, have you seen the with gen sims implementation of that macro, like generate run, like backward and comma? It's not that trivial to implement. I mean, you can do it like very easily, but then you have redundant calls to like list and append, and the implementation from JSCL have some rules to actually simplify and don't generate. I mean, generate kind of efficient and optimal code. And it's not that difficult in a way. It's like 200, 300 lines, but it was already there as public domain, so why not take it? And it's cool. It's like, guys still contributed to my project.
Ahead of time.
Yeah. But there are some limitations, and I don't know how to solve them. If you have any idea, please let me know. But for example, that thing is false in Common Lisp. But JavaScript doesn't have integers, only floats, doubles. So yes, you could wrap every number into a class or something, but it's not very practical, right? So I kind of gave up with that one. But maybe like I don't implement big numbers either. So maybe both things could be solved together.
Some kind of number in the library. Yeah.
But it would make it. So, I mean, it's not that like anybody's using it for anything performance. It's not critical, but anyway, it's a bit of a pity. Also, yeah, I think this is more important. Synchronous and asynchronous code. Like in JavaScript, you cannot stop the execution in the middle of a function. So.
Well, I think you can now with generators.
Yes, but that's not some function generator. So that if you want to use that, means that every function in Common Lisp should compile to a generator, every single one, because you cannot know if the functions that you call are synchronous or not.
Yes.
So it would be slow as well, but it could be worthy. I don't know. I don't really have like strong goals for the project. So if you think that it's worthy and you want to contribute, we can change it. But for now, just you cannot implement that. And the same thing for input and output. But it's quite bad because like the whole repo and everything is basically different in JavaScript than would be in Lisp.
You mean this would be slow as well because to
No, that you cannot, because every function in JavaScript that would read from input, for example, it would be asynchronous. So one of the parameters would be a callback.
Oh my god.
You could, of course, like transform everything into like continuation passing style, but again, it's like overkill.
Yeah.
So I think that's going to be always something that will be missing. Then we implemented some JavaScript interoperation. I think it's quite interesting. This is not the standard. We have this #J syntax that is not a reader macro because it's part of the symbols. So it's not a form. It can only like be a prefix for symbols. So basically, the reader says, "Oh, if your symbol starts with this, it will expand it into a form. This O gets actually." It means that it allows you to get from one root object like sequence or a path of properties. But it works very nicely actually. There is of course some transformation that you have to do. As I said, like strings are arrays of strings in JSCL.
So this actually prints the array.
No, because it will convert it automatically. The syntax #J will take all the parameters, convert them from Common Lisp to JavaScript, and then execute it. And then with the result that you get back, you do the opposite transformation.
But this string will be compiled.
Internally, yes.
Array.
Yes,
So
but before
if you
you
have this one, it'll understand. Oh, this is just a JavaScript.
Yes.
Code.
this string is not modifiable anyway, right? Because it's a constant.
yes, I don't optimize anything. The compiler is really nice. There is no optimization. So no. But it's nice, and there are some people doing some interesting things on top of it that it's not merged into the repository yet, but I had bindings for React and things like that. So it's cool. I'm just waiting because I mean functions call are the easy part, but what if you wanna like create a generator or a class or like JavaScript is evolving faster and faster.
Yeah.
So I want to be careful like which abstraction I choose for the SFI. So yeah. So some things that can be done because I haven't worked on the compiler for the last year at least, and then before that also a few years. But nowadays, like we could like probably the output could be better code. Like we don't have to have a function that compiles call itself, but there's an arrow function. It could be shorter. It's important because the output of the whole thing is like 1 megabyte of thing right now.
Yeah.
Yeah.
That's not so much.
And it's tricky because you want new functionality, but that grows and grows. And I want to make easy like generate applications because that's an interesting thing. We can use the JavaScript tooling. So for example, I was thinking maybe I can remove completely the code generation part, just generate ES3, the JSON representation of the JavaScript syntax, and then use Recast or Babel or any of those libraries to actually generate proper JavaScript. Or you can call the Google Closure compiler to optimize, like Closure script does. I don't know, there are many things, like, source maps could be much appreciated as well. But all those things are quite complicated, like, for example, how would a thing and a weight interact with dynamic bandings? Nice. So it's very easy to add something that, it works most of the cases, but then it breaks very badly in others. I think we're getting close to the end, but some things that are missing, and I would really appreciate like some help. like every time that somebody creates a pull request or something to the project, I get motivated and I also contribute.
So do you have stuff like close?
Sorry?
You have close, the Common Lisp object system?
That's missing. That's
missing.
the first thing that's missing.
Sorry.
Yes. Of course, like, you are not supposed to implement it yourself. There is an implementation from the MIT as well.
Yeah.
It's called like portable close, something like that.
Yeah. PC.
The problem is of course that all implementations, BCL, CL, I think CL actually have their own implementation. Most of the implementations took it for the Common Lisp, but for many years they have been applying patches.
Yeah.
So all that is kind of lost when you take the like 30 years old already game. And there is also this project JSCL that is kind of like a
CIC.
It's like library for all the different parts of Common Lisp. But
the Robert Swan thing, you mean?
Yeah.
Or,
but I cannot really use it because most of the code is based directly on silos. So yeah, the goal was to bootstrap it. If I use that, you could generate code. You could use it in the body of the macros, but you cannot compile yourself. That's the biggest one.
you have structs?
Yes, they're not fully compatible, but yeah, we generate like the copy function. Almost all of it. I think what is missing actually that by default it generates this representation instead of like what we call a storage vector. We have like this maps directly to a JavaScript array, a storage vector, then arrays, strings, def struct, all of them compiles to a storage vector. But it's not implemented for this struct yet. I mean, there are so many functions. You just pick any from the index of the hyperspec, and probably something is missing, and just add it. So I just add it when I need them. Type system. That one, I think it's not that important anymore. I was working on that when I was trying to write this smarter compiler. But it could be nice. I don't know, like what can you use it for? Like when this, I mean, if you don't have silos. But anyway.
Well, you still want to check types sometimes.
Yeah, but you have like the specific function still. You have string p, you have integer p. Just you cannot use type p.
And you want to do that?
Yeah, and you don't have like
so
or.
type case there as well, so all is basic.
Yes, in case is kind of hard coded there. We have a few lists of values and we check them. Yeah, it's.
And you can have def type as well, for example.
Yeah. That needs to be done. Format, there is a very simple kind of format that's a few like a and 2 or 3 values. So placeholders.
Isn't there a public domain implementation of that too?
I'm not aware of that.
Yeah.
Probably.
Yeah.
I mean, I have also taken a lot of code from JSCL, especially for all the helper functions and list functions. But and the one from JSCL is extensible. The format one. Yes.
Yeah.
If I remember correctly. But that means that it's more complicated to port it. What else is missing? Yeah. Big numbers, rational, complex numbers.
You have keywords?
Yes.
You also use them in the lambda list. And,
yes.
You have something like destruction and bind and stuff like that, yeah, right?
Yes. Actually, the destruction bind is better supported than the function lambda list.
Yeah, destruction. Yeah.
There is like a few edge cases. I learned this like recently. The lambda list of functions, you can pass a special variable as well as an argument.
Yeah. And have it bound. Like
and it will be bound automatically. And it's like, that's not supported. Yeah. So you will see a lot of places in the code where I have to receive an argument, and the first thing I do is let to the special variable.
I see handler case and handler bind as well.
Yes.
Nice.
Yes. I mean, you have to run a loop on top of it. I port it, but I have no idea how loop works internally. But it works.
Yeah,
I mean, it's a big library, so you need to be very complete if you want to support that.
I think it's a very good sign for interpreter, right? If something works and you don't know how it works.
Yeah, I mean, if I knew how it works, I would have probably just written that and not import it. And many other things. So please, help. It's a lot of fun. So that's it. You have any questions?
couple of questions.
Yeah.
First is about Babel and other minifiers. So have you tried to compare the output? Because of course, if you add type annotations, code could be compiled efficiently.
Yes. So, well, I think the minifier will not remove the type checks, right?
Well, if you use Google Closure compiler, then it will take it into account. So
Okay. Oh yeah, that one yes, but not the smart the dummy minifiers. But I have run it through the Google compiler.
Yeah.
But they have like different modes, like more or less aggressive. I'm putting is the most aggressive one. That is, I think, is the one that
yes.
Closure script is using.
The advanced.
Yeah. But it helps. At least it makes the bundle way smaller.
And another question is, to which version of JavaScript do you compile?
5. Like
5.
like
Pre-Equus 6.
yes.
What do you think? Which modern features of JavaScript could have made your compiled code shorter or like much easier?
Yes, definitely. But yeah, so when I started this, there was no JavaScript like 2015 or anything like that. But yeah, I would totally be willing to include it. Anything else?
It would be interesting to run JSCL on top of CL JavaScript just to make things more recursive. And then maybe JSCL once again.
So something I
Doing
didn't
it
say,
until
it
dies,
also supports Node.js. But something, I mean, kind of cheating because when I say that the goal was to bootstrap the project, it works, the compiler works on runtime, you can evaluate things in the repo, but I have never passed the whole code to the repo because there is no file system implementation, so I cannot read the files.
Oh, you don't have file.
So that would be also an interesting project.
But you can use synchronous functions from Node.
Yes, yeah, you could do that. But the Node support is also quite recent. Because the thing is, and that's also something interesting. So you have this introspection in Lisp, right? The image is there. Initially, I had all these variables that I generate, and they were available in the browser in the global scope. But that doesn't work in Node.js. You cannot have access to those variables. So I changed the compiler to put all the internal variables into a hash table, so you can change them. So, thank you.
Very nice. Thank you.